The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so this is the second last lecture on trusses. Then we get a holiday on Monday. And then after that, we'll be into Chapter 3. I thought I'd write down, just in case it's any use to you, the 4 problems that I intend to include with the next homework. That won't be due for quite a while, a week from Monday. So these will be the problems on trusses that come from particular trusses drawn in the book. And then there'll be some problems from the new material that we do next week. So trusses, and really two main jobs for today. One is to identify this matrix A, the strain displacement matrix or the stretching matrix. How far do the bars stretch? Everybody remembers A is going to come in this step if we have displacements. Then of the nodes, like this would be like a U1, this would be a U1H and a U1V. This would be a U2H and a U2V. So there are 4 movements of the ends of the truss and of one particular bar, and it'll stretch that bar. And the question is how much? So that will be one row of A. So this is, if we follow one bar, you remember in the matrix A, there's going to be a row for every bar. So a row for each row of A for each bar. And if we track down one of those rows, we'll have the idea. And then, of course, at the end, we'll maybe be constructing A without a sort of a free A. And then at the end, any fixed displacements that will knock out columns of A. So that's one job. And then to see, so the A is going to be a little more messy. It's because we're in 2 dimensions. So compared to the network problems and the line of springs, now we have more happening. We've got more columns because every node has now 2 unknowns, the horizontal and vertical. So A is kind of bigger, and therefore A transpose CA, you might think it's going to be hard to see what's going on, but you'll see the right way to look at A transpose CA is a bar at a time. That's the nice fact about A transpose CA. I might focus on that first. And then comes the fun part. I'll draw some more trusses that may or may not have mechanisms. They may or may not be stable, and we can try to identify the mechanisms. Actually, as before, we'll do it by engineering instinct rather than by solving. I mean, in principle, we could always use elimination or ask MATLAB or any other system to do it and look for the solutions to AU equals 0 and decide, are the columns of A independent? In that case, the truss is stable, this matrix is invertible, we know all the good possibility, and then there's the more interesting possibility of having some solutions to that, in which case that matrix will be singular. There'll be some modes in our big system that will cause it to fail. But it's kind of fun to find those. Okay, while I've written A transpose CA, may I remind you about a good way to do that multiplication. Okay, so I'll just imagine, I'm just putting a number. Here's going to be the matrix A. So the matrix A will have a bunch of rows, row 1, row 2, so on. these rows will correspond to bar 1, bar 2, and bar 3. Okay. Okay, then we have C. So that's a square matrix. That each bar has a spring constant, so C1, C2, C3. And then we have A transpose, and those rows are columns of A transpose. So that's the sort of picture of A transpose, C, A for a 3-bar, 3 bars only. But the point is made right here. There is a row of A for every bar, right? Because our matrix A is m by n. There are m bars, a row for every bar, and it tells us how far that bar is stretched. And we'll figure out what its entries are. That's our main job. I'm just looking ahead. Suppose we've got that row, and that row, and that row. So a row for every bar. Now, here I've taken 3 bars. Now, how do I multiply those matrices? Well, I can do it different ways, but here's a cool way to do it. The way I want to point out is column times row. If you multiply matrices, you're allowed to, and the effect of C1, C2, C3 is going to be very simple, so I'm really paying attention here to A transpose A. If I want to multiply A transpose A, I can do row times column as usual and get one number, or I can do column times row and get like a whole little matrix, and that's the bar 1 matrix. It's the element matrix, and that's how finite elements will be assembled, and that's why I keep mentioning this point. So the way to do that column times row thing, and then of course that C1 just multiplies that row, that'll be C1 row 1 transpose, that's the column, times row 1. That's what's coming from bar 1. That column multiplies the C1 and that row. Do you see how nice that's the element matrix associated with the first bar. And then there'll be a second column times the C2 times the second row, so plus C2 row 2 transpose row 2. That's a matrix again, plus C3 row 3 transpose row 3. I focus on that because you don't think of this as the way to multiply matrices, but it's really a nice thing to notice, and it's better to notice it now when we have 3 bars or something than in a big finite element code. Yeah, so this is, just if I complete this thought, this I would call a 1-bar matrix. That's the matrix A transpose A if there's only 1 bar. Actually, one of the problems at the end of this section is find the element matrix for 1 bar. And I guess it's about what we're going to get to when we do that 1 bar. Do you remember what it was just to connect this thought, what was the little matrix in the case of networks? So in the case of networks, there was just 1 unknown for each, not 2. So for networks, I'm just going to put down and you'll recognize it immediately. The little element matrix was the C for that, and there was a 1, minus 1, minus 1, 1. Do you remember that guy? That was the minus 1, 1 from a row, minus 1, 1 from a column. So this was exactly C times the minus 1, 1 from the column times the minus 1, 1 from the row. That's where this simple little matrix came from. And you remember that, so what's involved in creating this big A transpose CA is just create all these little pieces, which are like this, but they're going to be a little bigger. In fact, in a minute I'm going to ask you what size they'll be. Well, they're really big matrices. There are a whole lot of zeros there that I didn't even put. Zeros are there for rows and columns that aren't touching this particular edge. And again, this matrix, there'll be all kinds of zeros in A, because a typical row of A, bar 1, is going to have non-zeros only for the, what's the size, what's going to be, how many non-zeros in a typical row of A? Getting the count right first is like half the battle. How many non-zeros in a typical row of A? This was the network case where we had a couple of nodes and they were connected and we had an unknown at each end. So 2 unknowns were involved. The little matrix was 2 by 2. It properly has lots of zeros for all the other nodes that are not involved. And then that matrix kind of gets assembled, is the word I think usually used. All these little guys get assembled, you know, pasted, stamped, I hear as the verb sometimes now. Take these little matrices for this little element and stamp them into the big A transpose CA. You know, this is the C1, so this gives the C1s in the matrix and the C2s and the C3s. All right, now just before I'm like doing this preliminary before I write down anything, the exact row. What's the size of, for trusses, how many non-zeros in a row of A? So that's my question. How many non-zeros in a typical row, like for that bar, non-zeros in a row of A? So A is the matrix that tells us how much, that row of A is the row that tells us how much this bar stretched when this moved along by UH1 and up by UV1, and this moved along by, say, UH2 and up by UV2. Well, I've written all those in so that you can tell me this number. How many? What's your guess? When I tell you, you'll say, of course. How many U's are involved in the stretching of that bar? 4. 4, exactly. Instead of 1 at each end, we have 2 at each end. So the answer is 4. How many? The answer is 4. And now the only remaining question is, what are they? What are those 4 numbers, the 4 non-zeros in the row? So let me, so let me just answer that. They are. So here's that row. So we have two non-zeros associated with it. Well, the way I've numbered these nodes 1 and 2. Since I've numbered them 1 and 2, the non-zeros are going to come right at the start. And then a whole lot, then this is all going to be 0 after that. Because those will be nodes 3, 4, 5, whatever, that don't involve bar 1. So bar 1 just connects node 1 to node 2. Now, what do you think? Well, let me put in the key quantity here. This bar is at an angle. It's at an angle theta. So there's a theta, angle theta. Okay. And so that angle is going to enter these things. In fact, here's what you get. You get, I think, if I put the 1 up there and the 2 down there, let's see, what am I thinking now? I'm thinking if U1H is positive, that's going to stretch the bar. That's a positive stretching. So I'm expecting a positive U1H to give me, I'm expecting that sort of to come in with a plus sign. Now, suppose the bar is horizontal. Suppose the bar is horizontal. Then how much does the U1H stretch it? It stretches it by the whole U1H, right? If the bar was horizontal, So theta equals 0. I'm just doing these. We got to sort out this theta angle stuff. So here's my thing. If the bar happens to be horizontal, then that stretching by UH1 will completely stretch the bar. If the bar happened to be, and of course this would. So that for a horizontal bar, I'll just be back to this stuff. I'll have a 1 and a minus 1. I'll have oh yeah, remind me about that. Why doesn't U vertical, for a horizontal bar like this, why does this one not stretch the bar? You remember that from last time? That was the little bit of trig that we did when we forced ourselves to stay linear. So we dropped the second order correction that would come from going this way, right? Yeah. I mean, you must have noticed, like, walking. Suppose you want to walk from here to the end of the bar. Okay. Well, if somebody moves the end of the bar forward, you have to take those extra steps. The bar really stretched. But if somebody moves the bar this way, then the extra bit of length is much less, right? In fact, it's 0 to first order, right? This is like taking shortcuts when you walk across the courtyard. Okay, so when the angle's theta, I'm only expecting a 1 and a minus 1 on the horizontal and 0s on the vertical. Okay, now I'm ready to write in. I think when the angle's theta, any theta, that was when the angle was 0, I think we get a cos theta. Doesn't your instinct say that this is on the U1, U horizontal one, and then the U vertical one? You tell me what these should be, and then we'll make. What do you suppose is the entry, second non-zero, the one that corresponds to a vertical movement? Here it would be, for a horizontal bar, when theta is 0, I'm going to see a 0 there. But if the bar is at an angle like this, what am I going to see? Everybody's going to get it right. What do I put in there? Sine theta. What else could it be? Right. Okay. Sine theta. And now what about the next guy, the other end of the bar, UH2 and UV2? Those are the other two non-zeros. What's your guess for UH2? If I move this forward, what's this change in length of the bar? What would your guess be if that goes into there? Say it again? Minus cos theta. Minus cos theta. Right. Yeah. The movement of the other end, like if I move this guy a little bit to this side, that will shorten the bar. Right. So forget about that one. If I move this over, the bar becomes shorter, and the cosine tells me the key number there, how much it becomes shorter. If the bar was horizontal, the cosine of theta was 1, it counts 100%. If the bar is vertical, and I move it horizontally, it counts 0%, because the linearity says there was no first order change. And now tell me the final non-zero entry, and I see I didn't leave much room for all the zeros. Okay, what's the U2V entry? Minus sine theta, of course. And then come all the zeros for whatever other joints are not involved with bar 1. So let me, maybe to make this picture best, I should move that over where it belongs. Now, if I add up along a bar, add up the 4 numbers there, what do I get? 0. You expected that, right? If the bar in fact, if I add just that and that, I get 0. If I add that and that, I get 0. Just the way I got 0 here in the incidence matrices. The column of all ones is certainly going to solve AU equals 0 unless the supports remove those. Of course, if the supports don't allow all ones, because some have to stay at 0, then I could have a stable truss. Okay, that's a typical bar, a typical row. That's a typical row. Okay, and now maybe, let's see, while I'm on the same subject, what is the size? What does this thing look like now? This is in A. This is in the matrix A. And now I want to ask you, before I even come back to all this stuff, what about in A transpose A? In A transpose A. A transpose CA, the whole deal. The element for the little matrix, the element matrix, can I call it that? Or the one-bar matrix, say call it the one-bar matrix, is what? So I want this would be typical, C1, row 1, transpose, row 1. That's a typical guy. And how many non-zeros in that? Multiplying a row, multiplying a column that has 4 non-zeros, times a row that has 4 non-zeros, times a number, which is just fine. How many non-zeros are going to sit in this element matrix, this one-bar matrix? 16. 16 non-zeros. And they're going to be, they'll just be, I have cosine sine minus cosine minus sine, multiplying cosine sine minus sine, and all multiplied by C1. So that's the matrix, and you see what it looks like. C squared, CS, so on. 16 guys. So we have 4 squared as our element matrix, where here we had 2 squared. And in finite elements, when you get to elasticity, and you've got triangles, you've got triangular elements, then there are 3 nodes involved, so you're up to higher numbers. But this gives you the idea. And remember that this 4 by 4, the way I've done it, the way I've numbered it, 1, 2, happens to sit up in the upper left corner of A transpose CA. But can you sort of imagine how the code would be written? The code would be written. Take each bar, and what do I have to know about the bar? Yeah, just imagine a code that would do trusses. Actually, the final problem that I'm not assigning in this section says, what would the code be like? And can we just have a think about what the code would look like if we were to write it? What would the input have to be? What would I input for each bar? What input do I need? I need, for this bar, I need to know, and for the whole truss, what do I need? What do I have to tell? What's the information that I need for the whole truss? I have to know the positions of all the joints, right? So I'd have to know the coordinates of that, x, y, the coordinates of this one, x, y, x1, y1 for joint 1, x2, y2. So I'd have to have a little list of, what would that be, m by 2? I have, n by 2. I have n, yeah, what do I have now? Think of what information do I have to report about this truss? I guess I have n, capital N joints, and I need 2 coordinates, x, y, for each position. So that's n by 2 list, okay. And then for every bar, what do I need to tell it? What do I need to put in the code for a typical bar? I certainly have to put in the C for that bar. And what else do I need to know? I need to know which joints it's connecting, right? I have to tell the system that this bar is between 2 and 1, 1 and 2. I have to tell it which pairs. So I guess I have a list of m bars, and for each bar I must tell the system the 2 node numbers and the C, the stiffness, the constant for Hooke's law, right? Do you see this picture? Just sort of visualizing, creating a code here. And then the code would do all this. Oh, let's see, have I given enough information to find theta? Or do I have to input theta also? No, I told you the positions. So it'll figure out cos theta and sine theta. It actually won't figure out theta. That's always a dumb thing to do, to find the actual angle. Cos theta and sine theta is the quantities we want. So given that position xy and this position x2, y2, it would know cos theta and sine theta. And having drawn this picture allows me to make once more the key point about small displacements. What's the angle of the bar after it's moved, after it's displaced? It was theta before it was displaced, and the angle after is theta. To first order, the angle doesn't change, because these are little tiny movements of the ends. I've drawn them much bigger than they should be drawn. They're little tiny movements of the ends so that the angle is not significantly changed. Otherwise, we're into geometric nonlinearity, and that makes the problem much, much harder. Okay, are you seeing sort of the picture? I guess what I haven't completely, I really depended more on your intuition than on a calculation to say that these are the 4 non-zeros. What did I ask you to do? I asked you to check that that was right in the extreme cases, like if theta is 0, the bar is horizontal, then we just have a 1, 0, minus 1, 0. Vertical isn't happening. If the bar is vertical, so that the angle is 90 degrees, then we would have a 0, 1, 0, minus 1. Everything's vertical. And the book draws a little picture and computes delta L from these 4 small movements and takes the leading term, and sure enough, it produces that row of the matrix. Well, gosh, I talked real fast though. But do you think you could now create the stiffness for, if you had a real truss, you could create the matrix A for it. C is simple, it's given to you. You could create A transpose CA. You might just want to write the command as A prime star C star A or something and let MATLAB do the thinking. But I wanted you to see how this 4x4 piece appears in this product from each bar. The 16 non-zeros will appear in different positions, and you told the code what those positions are. You had to give the code a local to global picture. This is the local picture. Watch 1 bar. Then it has to fit in this big n by n matrix, and that means you have to know, well, what edges, what joints was that bar connecting? So which positions do these 16 non-zeros assemble into? Okay. That's some time devoted to a job that I actually don't plan to require you to do, creating this truss problem. What I think is kind of more fun, and that's these homework problems would deal with it, is part 2 of the lecture, going back to mechanisms, and now thinking about more complicated trusses. We now, in principle, could find the solutions to AU equals 0 because we now have constructed A, and we could get MATLAB to do the work, or Python, or whoever. But can I go to part 2 now and draw a truss and ask you about the mechanisms? Let me, let's see. I guess somewhere in the problem set, but not one of the assigned ones, is suppose that's my, start with those 6 bars and 6 joints. So these are 6 joints. And, okay, as it stands, how many, oh yeah, it's a good question. As it stands, what's the shape of the matrix A? How many rows has it got? So as it stands, so I'll call it, shall I call it A0, for no supports have been added? A0, just the full matrix, is what shape? 6 by 12. Good. 6 by 12 is 6 by 12. Okay. Of course it's not stable. We know that. We haven't supported anything. So how many, in a typical case, how many solutions to A, so I'm going to ask you, how many solutions to AU equals 0? And what's your guess? 6. Got 6 equations. We've got 12 U's. 12 minus 6, so this is going to be 12 minus 6, or 6 solutions to that equation, is what I would expect. It could be possible that these 6 equations are not independent. If they really drop to 5, then this would bump up to 7. I don't think it's going to happen here. Okay, now can you describe those 6 solutions? Not with numbers, just with, tell me. I hope you can, because I can't right now. Okay, 3 of them we know. So what are, with no supports at all, what are three rigid motions? And what are they? The whole truss could move to the right, the whole hexagon. It could all move up. It could all rotate about 1 point. All 3 of those would be movements, displacements that don't stretch anything. Okay, 3 rigid motions. Across, up, and rotate. Okay, and I can get rid of those by supporting some nodes. But let me see. I don't know what's going to happen. That's when I describe this topic as the fun one in 18085, it's more fun for you than for me, because I draw something like that and I start worrying. Can I think of 3? How many mechanisms to look for? 3. That's a big number. I bet you I can find 1, but you guys have got to. All right, tell me some mechanisms. Let me try to draw them. What would be one mechanism? Oh, geez. Collapses, yeah, somehow. What do you want to, how shall I make it collapse? can squeeze in. Yeah, maybe that's the first one. This guy comes in. This guy, what does that do? Oh. Yeah, let's see. I've got 15 minutes here. I could pull that board down and draw another one. What is this one here? Let's see. If that comes in, do these guys have to go up a bit? Yeah, because that angle is not 90 degrees. So we've got a first order change in this. So this comes in a little. This goes up a little. This guy maybe stays straight. Would you go for this? I mean, just please say yes. Something happens there, right? These things go in and those go up. Could you create the, I mean, if this was a, equal side, regular hexagon, you could put in all the numbers for all 12. I would be looking for 12 numbers, 6 joints, and they each have 2 U's. So that wouldn't be so simple, but you could do it. Okay. So that would be 1. I'm looking for number 2. What would be another one? So sort of squeezing in like whatever. What do you think? Any others? Maybe that's possible. Maybe I just look at it. You think that would work? We could hope those were independent, but I wouldn't put my life on it. If I, have this squeeze in, and this squeeze in, I would worry a little bit. I can see another one. And can you? Yeah, thanks.
Half or
fold it in half.
Or you could fold it along. I guess that sort of gets into 3D. But
yeah, we got to stay in the plane, right?
Instead of both sides coming in, have one side go in and the other go in the same direction as well.
Instead of what?
So you've squeezed the left side in.
Okay.
Now squeeze the right side out instead of the right side coming in as well.
Squeeze that out. Yeah. Good. Number 2. And then I can see, here's one. Here's an easy one to think of. Leave these 3 alone and just rotate these guys. Bring this down, right? Bring these 3 vertically down, or something. You see why it's sort of. Did you like that one all right? It seemed simple to me looking at it. Just leave these guys and, rotation, let this turn down, this turn down, let's say, and this go down. Yeah, maybe those would all drop by the same amount. Maybe. Okay. So anyway, whatever. Let's put some supports on and get these numbers down to where they. So let's support, as usual, the bottom guys. Okay. So different problem now. I won't call it A naught. I'll call it A. I'll ask myself, is it stable or unstable? The matrix is now 6 by what? 8. 8, right? Because I've taken away, I have 4 reaction forces, 2 at each support, horizontal and vertical. And I've got 4 free nodes. And yeah, 6 by 8. Let me put in, well, so 6 by 8, what am I expecting now? Any rigid motions? No, no rigid motions now. How many solutions am I expecting? 2, I think, probably 2. Okay, how many mechanisms? Well, no rigid motions, so probably 2 mechanisms. Now, can we find two mechanisms? All right, this is like more reasonable. We can see whether whether we get two mechanisms and whether they're really different. Okay, what are the mechanisms now? These guys are fixed. So forget my little sketch here and think again. What do you see? All right, let's have one mechanism. What would one mechanism be now? There have to be two. What do you think? Sit on it. Yeah, all right, bring these guys down, and then these guys will go out. Is that it? Okay, so mechanism number one, sit on truss. Okay. All right, now, I don't know what number two is. That's why I'm taking time.
If you were to hold one of the side ones and rotate it like in the previous case.
Yeah, or could we do this? Could we bring these guys in and let's go up? It's the same thing? Okay, so squeeze truss. Squeeze sides. Is that the same thing that I had? Is number one the same as two? Oh, geez. Okay. Is that what everybody is agreeing with this? Okay, so I didn't get it. Number two was no good. Okay. All right, what's a better number two? Hold an edge. Like that one?
Yeah.
I'm just doing what you say. I'm not.
And then the other three will rotate about same as the one you mentioned earlier.
Just this guy rotates like so,
All three of them will rotate.
and this guy will rotate, and this guy. That looks pretty good to me. Good. Is that correct? Should we say that one again? So the first one was when these two came down and these went out. Right. Okay. Okay, and now your suggestion is you picked on this guy and held it fixed, and then this one came down a little bit. It'll, of course, how will it move? It will move perpendicular, right? Small movement. The bar is not going to change length. That's the whole point, right? The bar is not changing length. So the movement must be a simple rotation around here, okay? Right? And of course, again, you might say, well, the bar really did change length because that's not quite the same as that, but then again, that's my second order business. Okay, so that one came down, and what did this one do? Came down the same. Okay, and this one, it also moves. What is that? I guess let me, so okay. What am I going to call this one? Fix one, yeah. Fix one node. Yeah, that makes sense, I guess. Fix one joint, yeah. And then rotate the rest. I think that would be possible, yeah. Okay, a small prize for anybody who maybe handwritten a picture of two really nice mechanisms. Somehow this one seems a little unsymmetric in a problem that's so symmetric. So I would guess that somewhere along the line we could find a kind of more symmetric one. But I don't see what it is right now. Yeah. Can the whole thing rotate a little? Could that rotate? Could the whole thing rotate? Yeah, maybe it could. This guy would go up. Yeah, maybe that's possible. That somehow got everybody into the action. Or so maybe or I'll put or rotate. Okay. So you see what questions you get into. May I just draw a different truss so those homework questions are other trusses. Here's one that I drew in the book itself. may I draw this? I called it a tree house. Okay, so I have, so here's one that's actually in the book. And it's got a couple of bars going up and one over. So that's the start. Then it's got a diagonal and that one. And then here comes the tree house. Okay. Right. Okay. Well, just to get, let's again get the count right. So what's the matrix A for this tree house? A is how many by how many? How many edges, how many bars are you seeing here? 1, 2, 3, 4, 5, 6, 7, 8. 8 bars. And how many unknown displacements? 10? We got 5 joints that are not supported, and each one has 2 unknowns. Yeah, so A is 8 by 10, so I expect 2 mechanisms. Okay, so again, I'm looking for 2 mechanisms. All right. Okay, what's one? Yeah, it's what? This guy just falls, right? This looks, unfortunately, very much like the tree houses that I built for my kids. Well, so linear algebra sentenced them to fall, right? Okay. Okay, that's one. I probably propped it up with one more bar, but of course that wouldn't be enough because it's got 2 mechanisms. So if I make it 9 by 10, I haven't saved the kids, right? Okay, but let's, with 8 by 10, what's the other mechanism? The whole thing could turn, nothing preventing turning here. They can't move, but they could turn. So the whole thing could go over, right? The whole thing could just, that would be a horizontal movement of all 5 nodes. A horizontal of all 5 nodes. And again, slightly downwards, but that's a second order effect. Right. Okay. So that's the second truss. Okay. So this is really like practice for discrete problems for the problems of plane elasticity. And the point is that there are 2 unknowns for each point if we have differential equations. So the differential equations of plane elasticity are not really simple. They're not really simple. And 3D elasticity even more, because we've got movement. The points are physical points, and they can move 3 ways, and it gets quite interesting, and those are the major problems of computational mechanics. Okay, let's say holiday time, and I'll see you next Wednesday for Chapter 3, which moves to partial differential equations.